Calculus, video 70, more on the fundamental theorem of calculus. So in the last video, I neglected to write down the formal definition of the fundamental theorem of calculus, the formal theorem here, so let's write this down. And one part that I missed that I should not have is this is only going to work if the function f, lowercase f, is continuous on the interval. If the lowercase f of x is not continuous on the interval, then we cannot use the fundamental theorem of calculus. So if f is continuous on AB, then the integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a, where capital F of x is the antiderivative of lowercase f of x. That is the fundamental theorem of calculus. Remember, we're using this to find the area under the curve that we have rewritten our sum or our limit as the largest partition, the largest subinterval goes to 0 of the sum I equals 1 to n of delta xi f of ci. We've said that is the same thing as this integral from a to b of f of x dx, which we've now found is capital F of b minus capital F of a. So we're still talking about the area under the curve, but now we're doing exact area under the curve. This is the exact area under the curve. All right. Let's try an example. Find the exact area under the curve of f of x equals 3 squared of x on the interval from 4 to 9. So while it's not necessary for you to draw a picture for each of these, it does help visually, I think, a lot of people. So we'll draw a picture. Our function is f of x is equal to 3 squared of x, so that would look something kind of like that. And we will be on the interval from 4 to 9. And so we're going to be looking for the area of this particular region, the exact area of this region. No more creating rectangles, no more adding the areas of the rectangles to get an approximation. We're going to get the exact area here using the fundamental theorem of calculus. Okay? And the way we do that is area is equal to the integral from a to b. Notice my a is the 4, my b is the 9. The a is in the lower bound here, the b, 9, the upper bound, so from 4 to 9, of the function 3 squared of x dx. We're going to use our knowledge of antiderivatives to find the antiderivative of 3 squared of x. I think it's easiest to rewrite this as 3x to the 1/2 dx. Now we'll undo the power rule by adding 1 to the exponent and dividing by our new exponent. So this is 3x to the 3/2 divided by 3/2, which is like multiplying by 2/3. No need to write plus c. The notation we use here is after we've done the integration, to find the antiderivative, we say we're going to evaluate this from 4 to 9. Okay, I see with some simplification that my 3's cancel. This is 2x to the 3/2 evaluated from 4 to 9. And so the fundamental theorem of calculus says I'm going to take the 9 and plug it in, and then subtract, plugging in the 4. So it will be 2 times 9 to the 3/2 minus 2 times 4 to the 3/2. Again, this is capital F of b minus this is capital F of a here. Okay, 9 to the 3/2. Well, the square root of 9 is 3, and then 3 cubed is 27. 27 times 2, 54. 4 to the 3/2. The square root of 4 is 2. Cubed is 8 times 2 is 16. 54 minus 16 should be 38. And the area under the curve here is 38. That's all there is to it. Okay, let's make sure we're understanding the notation here, because it's a very similar notation what we have here than what we had when we were doing antiderivatives, just strict antiderivatives. So let's make the distinction. If we are talking about the area under the curve, we can refer to that, we want to name it a definite integral. So if you see the word definite integral, that's area under the curve. It means that it's an integration with bounds. Bounds. You have a bound here, you have a bound here. It came from, right, a bound a to b. On the interval a to b creates bounds. We often call this the upper bound, and we call this one down here the lower bound. But the point here is the notation for to find the area under the curve is the integral from a to b of f of x dx. The answer to that will be a number. It'll be whatever number, like 38 before, for the area under the curve. Notice how similar that notation is to the thing we've done previously, which is finding the antiderivative. The antiderivative, called the indefinite integral, has no bounds. That's the only difference in the notation. They look exactly the same otherwise, but they mean two very different things. When you have bounds, when you have a definite integral, you are finding the area under the curve of f of x, and you'll get a number as your answer. When you do not have bounds, you're finding the antiderivative, or the indefinite integral, and the answer is a function, capital F of x, the antiderivative. And on that, you must have the constant c. Remember, the constant c canceled out when you were doing the definite integrals. When we did f of b minus f of a, capital F of b minus capital F of a, the constant c canceled out. But when we're doing antiderivative, you must have the constant c in there. Two very different concepts that we use almost the exact same notation for. So make sure you keep those straight. Let's do one more example here. How about the definite integral from 1 to 2 of 2 over x plus 3 over x squared dx. Pause the video, see if you can find the answer here, which will be the area under the curve of that function on the interval from 1 to 2. Okay, let's see how we did. I am going to rewrite this as the integral from 1 to 2 of 2x to the negative 1 plus 3x to the negative 2 to make my finding the antiderivative easier. So I cannot do power rule in this first one. I can't, if I add 1 to negative 1, that's 0, and dividing by 0 doesn't work. We remember that this is 2 natural log absolute value of x plus add 1 to negative 2 on the second part here, right here, negative 1, so negative 2 plus 1 is negative 1, divide by negative 1, actually then makes this minus 3x to the negative 1. I don't need the plus c, I'm going to evaluate this from 1 to 2. So maybe a little bit easier to write here, 2 natural log absolute value of x minus 3 over x evaluated from 1 to 2. So we're going to do f of b minus f of a. Right? So f of b is, I'm going to plug in the 2. That's 2 natural log absolute value of 2 minus 3 over 2. That's f of b. Minus f of a, I'm going to plug in the 1. 2 natural log absolute value of 1 minus 3 over 1. All right. First thing I notice, natural log of 1. What is the natural log of 1? Well, that is 0. So I have 2 natural log of 2. I don't need the absolute value anymore because the absolute value of 2 is 2. Minus 3 halves. Watch the signs here. Minus negative 3. Minus negative 3 would be plus 3. Negative 3 halves plus 3, that would be plus 3 halves. And this is a fine answer. If that's what the answer you want to give me, that's okay. That's a number. You can also put that in your calculator. 2 times the natural log of 2 plus 3 halves gives me about 2.89 if I were to round. Approximately 2.89, which is the area under the curve of this function 2 over x plus 3 over x squared on the interval from 1 to 2.